So we have a law that tells us how the pressure and volume of a gas are related. That would be Boyle's law, and those are inversely related. We have a law that tells us how temperature and the volume of a gas are related. That would be Charles's law, and those are a direct relationship. What's left? Well, just to relate pressure and temperature, and that's what Gay-Lussac did. Yes, that's his actual last name. This guy named Gay-Lussac figured out that the pressure of this vast of gas at constant volume, so we're talking about gases that are inside rigid containers, they're not elastic so that the volume can expand. You're keeping the volume the same, varies directly with the temperature in kelvins. Okay, and this should make some sense to you if you ever had an aerosol can like spray paint or hairspray, I guess, or something, and there's always a warning on it. It says, please do not store at temperatures above blah, blah, blah. Well, that's because the higher that temperature goes, the more pressure exists in that can, because again, that can is rigid. It will not allow for volume to expand, the volume of the gas to expand. So there comes a point where that container wasn't constructed to withstand that much pressure, and it will explode. So that's what those warnings are about, and this is where it comes from. Guy named Gay-Lussac, and he determined this law. So again, here's the math going on. This is a direct variation with the constant in there. And this is how we derive this. Let's look at our problem here. How do we use this? Okay. All right, so we have this gas. It's at a pressure of 3 atmospheres at 25 degrees Celsius. What's wrong with that? That's why I've circled it. Hopefully you said it has to be in kelvins. It does. So directions on the container warn the user not to keep it in a place where the temperature exceeds 52 degrees Celsius. Uh-oh, what's the problem with that? Again, got to be in kelvins. So what would be the gas pressure in the container at 52 degrees Celsius? So what's the big deal? Well, let's find out. So we want to know what would be the gas pressure. Trying to determine second pressure here. So we're going to do a little algebra so that we get P1 T2 over T1 is equal to P2. All right. And now we just plug things in. Our second pressure is going to be pressure 1, which is 3 atmospheres. And yes, you can put whichever units of pressure you want to in these equations. It's just that in the end, if the answer is a pressure, you'll know that that's the units you have to stay in. So we have 3 atmospheres of pressure multiplied by the second temperature. What's the second temperature? Well, it's going to be 52 plus 273, because we have to convert it to kelvins there, divided by the first temperature. What's the first temperature? Well, it is 25 plus 273. Figuring all of this out, we get, pop this into my calculator. Okay. And, oops. Forgot that parentheses, there we go. Divided by, all right, and what we get is 3.27 atmospheres. That may not seem like a big difference, but when you're talking about atmospheres of pressure, okay, you're talking about the entire atmosphere pressing down on the earth at sea level. So that's a large amount of pressure. So what we went up is nearly 1/3 of an atmosphere. And most of those containers are not made to withstand that much pressure. Okay, so well, that looks interesting. Looks like a student did that. We're not going to do this. Feel free to go ahead and do this yourself. And if you want to ask me if that's right, I'll figure it out and we can see if you got it right.